First, how do we express the forces? In general, we assume the existence of an idealized parcel or particle of fluid. We'll calculate the forces on this idealized parcel, and then we will take the limit of this parcel being infinitesimally small, take the idea of a finite parcel and move it to a continuous expression of the fluid or the continuum that is applicable in the entire fluid domain. The coordinate system that we will use to develop the expressions for the different forces will be a Cartesian coordinate system that's sitting at a point on the Earth and it is tangent to the Earth. The x direction will be positive from west to east. The y direction will be positive from south to north. And the vertical will be the local vertical as you look directly above you. We will, for the most part, assume that the Earth is a perfect sphere. This idea of the coordinate systems was introduced in an earlier lecture if you want to pay more attention to the nomenclature and the conventions of the field. The particle of the atmosphere that we're going to consider is rectangular or cubic in nature. We do this because it is something that we are familiar with, and it is a good way to derive these forces. Here is our cubical or rectangular parcel. So we've just drawn a boundary into the fluid. Here is the x direction. Here is the y direction. Here is the z direction, where again x is west to east, y from south to north, the z direction from low to high directly above you. We will assume that within this parcel there is a density, rho, which is mass per unit volume. The volume will be simply delta x times delta y times delta z. Again, a very intuitive way to think about the volume of a parcel in 3 dimensions, and therefore the mass of the parcel will be rho delta x delta y delta z, since rho is mass per unit volume, and here is the volume, and here is the mass.